Thanks for coming out. I think we're going to go ahead and get started. So this is Testing for Data Scientists with me, Trey, Causey. I appreciate that you've come to all sit in a dark, windowless room and talk about software testing. That either means you have very specific interests or it sounded interesting to you or something along those lines. But thanks for coming out. You can find these slides online. Sorry, I'm not supposed to move around too much. You can find these slides online at the URL there. I'm on Twitter at Trey Causey. So if you have questions that I don't get to or anything like that, feel free to tweet at me. And that's my personal website right there. So just kind of a little detail about who I am. By day, I am a data scientist at Datto, which is based here in Seattle. We build machine learning software, and we're also a sponsor of PyData Seattle. Nights and weekends, I'm kind of a sports analytics fan. Did my mic just drop out, or is that just me? Cool, all right. So nights and weekends, I'm a sports analytics guy, do a lot of sports data, do a little bit of that for pay and a lot for fun. So if you're into the kind of intersection of sports and data science, I've got a blog that's never updated, and you can visit it right there. Hopefully that's going to change very soon. Football season's about to start. All right, so what am I going to talk about today? It's really kind of two talks, and so probably some of you will be disappointed at one of these talks, and some of you will be glad that you came for the other section. The first half is going to be kind of like, well, what is software testing? Why do we want to do it? Why do data scientists particularly want to do software testing? Kind of what are the kinds of tests that we want to run on our software? And then a quick review of unit testing, which if you're already familiar with it, won't be anything new, but if you've never done any kind of software testing before, might give you a quick start on how to start testing. The second half is going to be a little bit of a bait and switch, and I'm going to say, actually, all this unit testing stuff maybe isn't great for a lot of typical data science problems, and I'm going to talk about why that's the case, and I'm going to show you some promising packages that are available in the Python ecosystem right now that start to address some of these things. So just let me know if you have questions, feel free to interrupt. I'm a fast talker, so you can also tell me to slow down, and I'll probably ignore you. All right, so if you're like me, many data scientists kind of started off in academia. So I was in grad school working on a PhD. I thought my life was going to be, in the library, like working kind of monastically on some like really important question. And I was going to be publishing a paper, and it was going to be amazing. And I was going to get patches for my jacket and things like that. And I thought my life was going to look like this. This is actually Suzzalo Library, which is here in Seattle at the UW. It's the graduate school library. And I actually really did spend a lot of time in that room. So for a while, this is what the life of a data scientist looked like for me. In reality, what it looks like for a lot of us is actually something more like this. And you're not kind of toiling away, living the monastic lifestyle. You're actually working with a bunch of other people. And a lot of those people are not data scientists. They're engineers, or they're in various other capacities. You're sitting right across from them. They have to use the code that you wrote and the analyses that you're working on, and you're not going to be there necessarily when they do it. And that seems a little crazy at first, because I think probably in the past you were like working on a paper and you got to an analysis and you wrote up that paper for publication. You submitted it to a journal. You had your hopes and dreams dashed when they rejected it, and then you submitted it to 3 or 4 more journals. And finally, after 3 or 4 rounds of revise and resubmit, you publish it somewhere. And then you were done with it, and you're like, I don't ever want to see that paper or that data again. Please get it away from me. I was done with it a month ago. So it's not like that anymore. Now the kind of code that you're writing is going to be reused a lot, and it's going to be like talking to other pieces of code, and it's going to be touching other pieces of data that didn't even exist when you originally wrote your code, right? So new data is going to be coming in via like customers, via your website, whatever. And so you have to think about how your code is going to interact with that data. So instead of a research paper, that you publish or try to publish and fail, or some kind of like bounded research project, your work now looks something like this, where you're getting data coming in from multiple sources, you're kind of building models on top of that data, you're iterating through that, and then at some point you're kind of loading the results of your modeling back into some other database somewhere, into some column store or something along those lines to be consumed by whatever. So instead of a research paper, you're now like predicting click-through rates, or you're making recommendations, or whatever. Or you're in scientific computing and you're kind of working at the intersection of both of these things. So now that your work looks like this, and your code is going to be touching a lot of different things that it didn't used to touch when you were working by yourself, you need to think about how to be a good citizen kind of that coding ecosystem. So all the data you're going to be dealing with is no longer academic data. It's no longer pre-cleaned for you. It's no longer like, it's not MNIST. It's not like, pre-processed for you and a million eyes have looked at it and you figured out like where all the kind of difficult and tricky parts of the data are, the data is now real, it's now messy, and you've written equally messy code to go with it because you probably weren't trained as a computer scientist. Maybe you were, awesome, but maybe you weren't, and you taught yourself to code as like kind of a means to an end. So you've written messy code to deal with messy data, and what you're doing in each of those steps is you're making assumptions, both about how your code is going to work, about what the data is going to look like. I've switched to data singular here, by the way, so if you're a data plural person, we can talk afterwards. What the data is going to look like, and kind of, how all those assumptions that you're making are going to play out. And a lot of times you don't realize you're making assumptions. So maybe at the modeling step, you're building a statistical model, and you're like, okay, well, I know some assumptions to this model is that the errors are normally distributed with a mean of 0 and a standard deviation of 1, or so on and so forth, or like I assume that the data is distributed IID. You have all these assumptions that you think carefully about, but when you're actually writing the code that that mythical 80% of your time, scraping CSVs, like you're not thinking about like assumptions you're making about the data as well. And you're not making assumptions about what's going to happen when that data and that model come together. So I want to encourage you to think about testing as a way to make those assumptions explicit. So this is all kind of inspired. A little while back, I wrote a blog post called Software Development Skills That Data Scientists Might Not Know They Need. And so this kind of came out of some thinking that I was having. So I work with primarily machine learning engineers now, and they're all like really good software engineers as well as machine learning experts. So it's terrifying, and will give you imposter syndrome. But they're really good software engineers, and there are like ways of like working on a collaborative software, like collaborative code base together with people, right? And a lot of people coming out of academia, particularly data scientists, don't know that they're going to need to do these things. So these things include like writing modular and reusable code, or like the single responsibility principle, or don't repeat yourself. These kinds of acronyms that you hear. Writing good documentation and comments, not like read data, build model, those kinds of documents. The documentation you probably wrote at some point when you were working on your academic research, if you wrote any comments at all. Things like distributed version control, and then testing and logging. And I think testing is kind of like, actually has its fingers in all of these other points as well. But I'm going to focus on testing for the most part. So I'm not going to give a comprehensive overview of what testing is, or give you tons of examples of how to do it, because Ned Batchelder did a much better job than I could do of that. So at PyCon 2014, if you want like a real deep dive into how to write unit tests and the kind of philosophy of writing unit tests, as well as how to use the unit test package in Python, I would recommend watching this. Plus, Ned is an amazing speaker, and it's just a good talk to watch. So I'm not going to give you that. I'll give you a very shallow introduction, which won't be useful to you. All right. So as data scientists, want to think about like, when do I start writing tests? Because you maybe haven't, raise your hand if you've never written a test for the code that you've written. It's okay. Everybody look forward and raise your hand if you've, okay. So a substantial number of you have never written a test before, and a substantial number of you are lying, but there are definitely people in the audience that have never kind of written tests for their code, and so they might think like, well, when do I test? When do I need to write tests for my code, right? So there are lots of different steps in data science, and we've all heard of ETL, the kind of extract, transform, load paradigm. Every single step there, you should be like writing tests for your code, extracting, transforming, and loading, because you're making assumptions about what the data that you're extracting looks like, what you're transforming it into, and how it's going to be loaded back into somewhere else. But there's also the modeling step, and this is kind of like the Wild West as far as testing goes, because it's not clear what it means actually to write tests for probabilistic algorithms a lot of the time. So I'm going to talk a little bit more in detail about that, but that's kind of, I would say the ETL part of this is kind of the first half of the talk, and then the second half of the talk is the modeling part. Anyone have any questions so far? I'm going to get my phone out because I need to know how long I'm taking here, and I have like no clue how long we're taking. All right. Perfect. So why do we write tests for our software? So people will say it's to ensure correctness, and then some people say, no, you're not ensuring correctness, you're having more confidence in correctness, and we can debate this, whatever. But basically what testing does is it helps you, find bugs. That's the kind of obvious reason you would write tests. It helps you check your assumptions that you've made. So I've kind of made multiple references to this. That's a hobby horse of mine. It helps you write simpler code because, as I'm going to show you, like unit tests and software tests should only be kind of testing one unit of code, hence the name, like one small piece of code that does one thing. And if you find you're having a hard time writing a test for your code, then it might actually be the problem that you might need to simplify your code to make that easier. But it also makes you a good citizen of working with the code base, and people have more confidence that the code that you are checking into their code base isn't going to explode when someone else is on pager duty, like at midnight on Saturday or something like that. And like I've had a lot of people tell me that, like, oh, I don't like working with data scientists because they write terrible code and they're not good citizens of the code base, and as a result, like everything breaks and I'm on call for it. So testing helps other people have confidence that you've thought about how your code might break and you've developed solutions for it. And I think ultimately, the nice thing about it is it helps you be surprised less. So that sounds boring, like we're all in a windowless room talking about testing, but it helps you not be surprised when you don't want to be surprised. So, because being surprised is never a good thing once your data is out there, or once your model's out there hitting production data, and so on and so forth. So make your life more boring. Boring is good, boring technology is good. So I've kind of been using the word testing and unit testing interchangeably for the most part, but there are multiple kinds of tests. So I think when most people say tests, they mean unit tests, and we're going to spend a little bit of time on those. But I think also for data scientists, some important things are regression tests, which is the most overloaded term ever, right? Oh, I found a regression in my data. You say that to a data scientist, what does that mean you found a regression in your data? Regression tests are when you find a bug and you write a test for it and you make sure that that bug never shows up again. So let's say you find a bug in your ETL code or your kind of feature transformation code or something like that, and for some reason it's introducing not a number somewhere or something like that. Well, you can reproduce those steps in a test and then make sure that when you change the code later, you don't reintroduce that bug at any point. Because probably you introduced that bug because you made an assumption, and you're going to make that assumption again because thinking is automatic a lot of the times, especially when you're writing code. So there you go. And then integration tests, I think, are super important for data scientists because they're basically the way multiple pieces of code talk to each other. So I'm going to talk a little bit about what that means, but that's kind of the crux of what I think a lot of what we do every day is we're having lots of different data sources talk to each other. We want to make sure that code plays nicely with each other. So we want to extract some code, build some features out of it, fit into a machine learning model, make predictions based on that model, and then feed those predictions back into some other database. All right, so this is the boring part for you if you've already written tests, but if you've never written tests, this is going to be your lightning fast introduction to what a unit test is. So as I kind of said before, unit tests are the idea of testing kind of one unit of code. So you can think of a unit as a function, right? So you just want to test one function, and that function should only do one thing, and you want to make sure that it does it correctly. So if you're creating a function, like I'm going to show you in a second, to compute the mean of an array, you want to make sure that that correctly computes the mean of an array. So this is kind of contrived, and it's not a very useful example, but we'll get to why that is. The idea is that it shouldn't depend on any other code that you yourself have written, because then it's an integration test. And then you also have the assumptions baked into the other code you've written baked into this code as a dependency. And third, these tests shouldn't require access to databases or APIs or things they should run locally and they should run quickly. And I know that might sound counterintuitive because I just said this is all about ETL and this is all about different kinds of data talking to each other, but we'll talk about what that looks like. So the standard kind of Python unit testing landscape looks like this. I'm a fierce PyTest advocate. I prefer it much more than unit test or unit test 2. I'm going to show you why in a second. There's also Nose, which runs test suites, Fixtures and Mock, which enable you to fool your tests or kind of simulate connecting to databases or APIs within your test. So you don't actually have to go out and hit the API when you're writing the test. You can set up a mock that makes the code think that it's actually hitting the API and returning some kind of response. So that way you can always run it even if that particular API is down when you're developing. So I want to talk about PyTests in the most detail. So here's a kind of simple example. I write a function called mean that accepts values, and we're going to return the sum of those values divided by the length of those values. What could possibly go wrong with this code? Yeah?
The list is empty.
The list is empty, absolutely. What else can go wrong with this code? Yeah?
Types of values.
Types of values, absolutely. What else?
I think length of values is 0.
Length could be 0, absolutely. So that'd be divide by 0.
Overflow.
Overflow, what else?
Here in Python 2.
Yes. Why do I have issues in Python 2? That's right. So these are all things this is literally the formula for the mean, right? But these are all things that could go wrong. And we haven't said what values looks like, where values is going to be coming from. Maybe values is an array that's coming in off the network, and I'm trying to find the average load for a particular device or something like that. Or maybe mean is data that I always have historically. These are things we would want to think about, but those are all things that could go wrong in this case. So I'm going to show you a very contrived, simple-looking test to get you thinking about how you would write tests for those different scenarios. So I'm going to use PyData Test because it's really nice, and this is a simple example right here. So in a separate module, usually you want to separate your test code from your application code. Usually, I create a function here called test_main, and there are what are called test discovery rules in Python. So if you name a file or a method with a certain test_beginning, all the test suites will automatically detect that those are tests and should be run. So here, I'm making an assertion. So this is the simplest kind of unit test. I'm asserting that the mean of this list of values would be equal to 2. That's clearly incorrect. The mean of these values would be 3. But you actually it's nice to see a test fail. So if you've never written a test before, I encourage the first test you write to be a failing test so you see what that looks like. So why do I want to use PyData and why do I want to use such a silly example? So I'll answer the first one because it's easier to answer than the second one. PyData has no boilerplate code for the most part. It's like you saw, it's just writing functions and making some assertions, and you can assert that certain errors will raise certain error messages, exceptions, and so on. If you were to use unit tests, which is the kind of ships with Python, the standard library, testing library, it's based on JUnit, which is the Java unit testing library. And so everything has to be encapsulated in a class that inherits from unit test.testCase. And then you have all this self nonsense and so on and so forth. So I really recommend PyData because it gets you testing quickly. And the cool thing about it too is if I were to run this code here, the assertion error would give me a meaningful error message. It would say, you're asserting that 2 equals 3, and that's clearly a problem. Here's the line of your code that happened at, here's what you expected to happen, and here's what happened. So it's getting back to this theme of making your assumptions explicit and saying I am assuming that this value is going to be 3 or going to be 2 in this case, and let's see if that actually happens. Okay, so kind of general philosophy of when and why you should test. So if you've never written a test before, the next time you change a piece of code, add a test to it. Make sure you didn't introduce a new bug. That's a good first place to start. You don't have to go back. I don't recommend going back to all of your old projects and writing a bunch of tests for them because probably you have more important things to do with your time. But it could be good practice. I don't know. I have mixed feelings on some of these aphorisms. But anyway, so test the outcome, not the implementation. So this is something important to think about that a lot of people don't think about at first. You want to test the answer. You don't want to test how you got to the answer. And the reason you want to do that is then you can go and change all the computation code and maybe make it faster and refactor it. As long as you're still getting the right answer, the test doesn't care. The test is just checking for the outcome. Now, I just said never, always, and these are obviously not good things to say. So there are going to be cases when you want to actually do these things, but that's fine. So the nice thing is you can go and change a bunch of code, run your tests. If all the tests continue to pass, you're in good shape. If you find a bug, add a test. And tests also help identify complexity. So something to think about, don't test code that's already tested. Scikit-learn, NumPy, SciPy have awesome test suites. You don't need to test to make sure that they're doing their job correctly, right? You need to test the code that you wrote is doing its job correctly. And don't have overlapping tests, because then if one test fails and the other one doesn't, you're kind of in a weird state of undetermined outcome there. So don't test code that's already been tested, test outcomes, not implementations. And every time you kind of change the code base, add a test for it. So there's this idea that I vehemently disagree with called test-driven development. I don't vehemently disagree with it, but I don't think it's appropriate for data science for the most part. Called test-driven development. And this is a kind of a movement. And there's this whole idea that what you do is instead of writing your code first, you write tests that are going to be run for when your code is done. And you write those tests so that they'll pass once the code is already written in, once the code is all written in, and your answers are correct. So you keep failing tests, and you keep changing the code until the test pass. So in this case, I would start with this test, except I would make this a 3. And I would keep writing, keep adjusting the actual mean function until I got to the answer I was expecting. I think this is a bad idea for most data science problems. So I think testing for data science, and this is kind of shifting to the second part of the talk, is a little different because a lot of times deterministic answers don't exist for your problem necessarily. You're getting probabilistic answers, right? And something else dangerous that happens when you keep writing tests, keep writing code to pass your existing tests is you get some crazy situations where all of your tests pass because you've made some strong assumptions about what the right answers are, and you've gotten so wrapped up in making those tests pass that your code isn't actually doing what it wants to do, what you want it to do, it's just doing what the tests think it should do. So, if you think about this from a machine learning standpoint, we actually have a word for this, and it's called overfitting. And this is when your tests, or you're basically your code, you're writing to previously written tests, and you're memorizing your past mistakes. So you're memorizing those mistakes, you're changing your code to make sure those mistakes don't pop up again. But what do we really care about a lot of times in machine learning models? What's going to happen in the future, right? So we don't want to overfit to our past examples and get kind of blinders on and say well, all these tests are passing now, so I think I'm in good shape. We should strive to avoid overfitting both in our models, but also in our testing. So I'm going to talk a little bit about how I think we can do that and how we can get around that. So probably we've all done this before. We've been lazy, not in the good functional way, but in the kind of like, 7 deadly sins kind of way. And we haven't been great about how we handle our data that we're building models on. So maybe we extracted the data we wanted once because the data is painful to extract and it's sitting in some really slow database or something like that. And we built a lot of models on top of that data. And we become very confident about our model, and then, oh crap, our new data set that we finally extract, it doesn't do very well on. Or we think that the data we've seen in the past is going to be representative of the future, and we weren't very good about cross-validation or a training and testing set, and so on and so forth. Or maybe, I know that we all do this, you pick some examples in the data, some specific samples, and you keep checking how your prediction is doing on them as you're iterating through building your models. That's exactly the kind of overfitting via testing that I'm doing. In fact, if you've never written a test, but you do that, you're like, well, I know the answer should be this for this particular line, this particular sample, and you keep building your model until you get that answer. You're testing right there. You're just running them by hand, and you're running them on one particular example. So we want to not do this. We want to get away from this. And I think that what I like as a data scientist, when I hear things about like randomness and probability, I get pretty excited. So I want to talk about how we can introduce randomness and probability into our testing as well, and I think it's really exciting. So I think there are better ways to move forward and better ways to test things. The first thing we can do is we can take a different approach to testing. Rather than thinking up these specific edge cases that we're scared about, we can think about properties that we would like the data to have and properties that we would like our kind of results for our models to have and test those instead. So those are the actual assumptions we're making rather than specific values. We can make assumptions about like what the data will look like, what shape it will have, what kind of type it will have, and so on. I was just in the Python 3.5 session before this, and one of the questions was, will it ever come to pass that the type hinting that's in 3.5 will allow data frames as a type? Because some people might expect their function to take a data frame as an input and a data frame as an output, and you want to make some assertions about the kinds of d-types that data frame is made up of, and so on and so forth. The answer was no for now, but I think there's someone in the room who maybe is kind of working on some stuff like this. And then finally, I'm going to talk about testing probabilistically. So I think there are 3 promising projects in the Python ecosphere right now that kind of get at the kinds of approaches to testing that I'm talking about. And that's not testing specific values. That's trying to be more robust about how we build tests. The first is unguard by Tom Augsburger, who's one of the developers of Pandas. And the idea behind unguard is for doing defensive data analysis. What do we mean by defensive data analysis? So I'm going to switch back to data R, plural here, because Tom did that, but I firmly and resoundingly disapprove of that. So the idea is that the raison d'etre is for on guard is that data are messy. So let's do some things about that. So I think this is a really promising package. It's very early in development, but great for ETL on changing data. So if you have constant data coming in and you want to make some assumptions about that data, this provides a really lightweight way of doing that, and it's built on pandas. So I'm going to show you what it looks like in just a second, but basically any function that you have that accepts and returns a data frame, you can just add some decorators to, and it automatically kind of tests for the assumptions that you have about the shape and type of that data. Or you can do it interactively using the pipe method. And if you haven't looked at the pipe method that's been added to Pandas recently, it's pretty cool. So it just kind of looks like this, pretty easy. So we have some function compute that accepts a data frame as an argument and returns a result, which is also going to be a data frame. And so we just have 3 decorators here that make our assumptions explicit about what we expect about this data. So this -1 means we don't care how many rows the data has, but we expect it to have 10 columns. So it's going to make that check for us. Should the data frame be monotonic? So for instance, I work with a lot of sports data. So like we would expect that the time on the clock is always going to be decreasing, or if you think about it as 1 minus the time on the clock, it will always be increasing, right? So you can make checks for that. Or if you have time series data and you want to make sure that the timestamp is always increasing, something along those lines, you can kind of make those assumptions and just quickly with the decorator right there, and it's going to test that for you when it runs. Or there shouldn't be any missing values. So say that you have an algorithm that doesn't like missing values, and you need to make sure that your data doesn't have any missing values, and the code that you wrote to get your data shouldn't produce any missing values. This is like one-liner right here. You can make that check explicit. So I think this is really cool and really promising, and it kind of just encapsulates a lot of the like ad hoc checks a lot of us do on our data as we're modeling all the time. But it kind of takes the cognitive like switching costs out of it. You're just like, oh, I just add this and it's going to do it for me, rather than me having to remember to do it at all the steps of my analysis. Is that a faithful? Awesome. All right. So the next package that I'm super excited about that's awesome is called Hypothesis. And this is based on Haskell's Quick Check. There's also Scala Check, which is the Scala version of this. I think there are other versions like JCheck. I can't remember if that's the Java one or not. But this is a pretty amazing idea, and I think this will appeal to the data scientist in you. So rather than testing for values, this is testing about properties. We want to make our assumptions about what our data looks like and the values that our function return explicit, and we're going to randomly generate data and do a bunch of tests. So we don't have to think of all the edge cases. We don't have to think about the data we want to feed it. We can randomly generate that data according to some specifications, either very loose specifications like what type it is. So it's going to test things like addresses. It's going to test things like strings. What happens if the string has Unicode in it and it's not supposed to, and so on and so forth. And it's going to do all this automatically for you. And it's pretty awesome. And the cool thing about it is that the author is slightly diabolical about it as well. He's a really fun read on Twitter. His thing is finding weird corner cases in Python itself as well as in your data and trying to find those as quickly as possible. So what happens if you have 2 nested lists instead of 3 nested lists? Or what happens if you have a tuple nested within a list? Or what happens if you assign just kind of all the edge cases that you don't want to think about, they're doing for you. And you can also give it specific values as well. So if you know that there's a value you're going to see a lot, you can specifically test for that too. So it works in a kind of similar syntax to on guard. We're just importing from hypothesis given, which is basically the assumptions we're going to make. And then the kind of assumptions are grouped into what are called strategies. And these are data types a lot of the time. So this test mean function here, I'm just saying, hey, give it lists of integers. So I want to test this function on lists of integers. And in fact, when you run it, the first thing it finds is oh, this doesn't work if the list is empty. So whoever said empty list as the first, I think it was you, yeah, first error, that's the very first error that it found. But then it kind of runs through a number of other cases as well. So pretty cool. And it comes with a really deep knowledge of kind of Python internals. So all the Python gotchas that we've all forgotten about and then spent a lot of time debugging code and realizing this is actually some gotcha in the language and so on and so forth. They're all kind of baked in. It's very flexible. And it has plugin support, so it's pretty cool for all different kinds of data. Ideal for code that's going to be accepting input from the wild. So say you're using free text entry that customers have on a form on the website or something like that, and you want to do some kind of LDA or some kind of text modeling on that. It is really good with free text and kind of really dirty data. The other nice thing is it actually just works with PyTest and Nose and all these other frameworks. You just need to add those decorators. And it works with Faker. Has anybody in here ever heard of Faker? This is pretty cool. Yeah, so Faker will just generate fake-looking, realistic data for you. So you can say, give me 1,000 addresses. And it'll give you 1,000 fake addresses. And you can specify it with locales and so on and so forth. So you're give me 100 fake addresses in the UK. And it would conform to those kinds of data types. It has a datetime plugin. So if you hate yourself when you work with datetimes all the time, it will also, or sorry, vice versa. You work with datetimes all the time and you hate yourself. It will generate all sorts of kind of diabolical datetime edge cases to figure out if your your program's actually handling date times correctly. There's so probably most importantly for data scientists, there's experimental NumPy support right now. It's on GitHub, but NumPy support is not a first-class feature right now. So I'm sure PRs are accepted. And then the last thing I'd like to talk about, the last package, is FeatureForge. And this is pretty cool. It's a testing package with machine learning and specifically scikit-learn in mind. So along the same ideas as, they're all decorator-based. I actually just realized this just now. Along the same kind of path as on guard and hypothesis, it's basically let's make our assumptions explicit but not feed specific values. So for instance, you can imagine we have some code here that creates, let's say we have emails that are stored in a dictionary, and the body of the email is stored with the key body. And so let's say we want to turn that into a feature in some machine learning model where the number of characters in the email is a feature or something like that. With FeatureForge, we can specify an input schema, so we expect body to be Unicode. Some output schema, we expect it to be an integer and non-negative. And then it's going to generate some fake data for us and make sure that those assumptions hold. So this goes back to the laziness, oh, you've got data you pulled out of a database. This feature creation code that you have works great on that code, but you know what? That database is going to be even dirtier next week. I guess, databases tend towards chaos. And so the data is going to be messier next week, and it's going to hopefully test for some of those edge cases for you. So it's specifically built with feature creation and machine learning in mind, you can actually create pipelines in the same kind of way that you can in scikit-learn, where you can build model training pipelines. You can build feature creation and testing pipelines, so it kind of becomes an integration test set at that point. It also, this is kind of weird, it seems like I actually haven't explored this very much, but kind of added on to is an experiments functionality, which is basically you want to run a bunch of different models with a bunch of different features, and you want to store the results of those models into Mongo or some other DB, and it's going to do that for you automatically and distribute those. But this seems kind of like a somewhat overlap with grid parameter search and randomized CV in scikit-learn already. But yeah, so pretty cool. I think the idea for all three of these is not contrived, not hard coding values, and making sure that like the randomness that in generating the data that you're running your tests with gets at the corner cases that you weren't thinking about. So I think it's not actually the case that it's easy to write tests for modeling. So I'm going to talk about that now. Last, probabilistic testing. So model testing is like, I don't actually know. I don't have, this is a terrible punchline. I don't have a good answer for this. If you came here for a good answer to this, I'm sorry. But I don't have a good answer for this because like a lot of times what's gonna happen, like you build a classifier, it's gonna output probabilities or something like that, right? And it's in production and you're putting those out, say every day for a bunch of customers or something like that. Like, how do you know if it's working or not, right? Like, it's actually not totally clear what it means for that model to be working. In fact, you can think about it in some ways, if it's like trying to get people to do something on the website, it's gonna get worse over time because people are gonna start doing that thing and your features are not gonna be predictive anymore, or so on and so forth. So what does it mean for these tests to pass? I think it means, what does the data that it outputs look like? So OnGuard provides a couple things here, like maybe we assume that it's gonna be monotonic in its output, or maybe we assume that our predictions are all gonna be within some number of standard deviations, or if it's a classifier with labels, that they're all gonna be within some set of values, or something like that. So I actually don't really know what the answer is, and I'd love to hear thoughts on this in Q&A or afterwards about what you think we should do. The caveats I'll throw in is don't test algorithms that you haven't personally implemented. This is redundant. You don't need to do it. Scikit-learn, SciPy, NumPy have really excellent test suites already. So you don't need to make sure that scikit-learn is doing a logistic regression correctly. If it's not, it's probably with your data. It's not with the scikit-learn. I mean, you may have found a bug, but it's more likely that you have some issue in your data transformation. Similarly, if you have implemented an algorithm by hand, both all of Pandas, SciPy, and NumPy also have testing methods. So numerical computing is tricky and sucks in a lot of ways, right? Because it's like, you can't assert that two things are equal necessarily because of, underflow and overflow and so on and so forth. So NumPy comes with testing methods to assert that two arrays are close, or that they're equal to some tolerance and so on and so forth. And Pandas has that you can assert a series is increasing monotonically, or that two data frames are equal, and so on and so forth. So use the testing tools that have already been built as it makes sense for you kind of in your model building workflow. So I want to open it up for Q&A, but let me tell you what I didn't cover. So the first thing I didn't cover is testing MC code, which is like, right? So if you are interested in that topic, I would recommend following Tim Hopper, who is trying to figure this out for himself right now. So he's at TDHopper on Twitter. I didn't follow things like continuous integration. So this is kind of the idea that like every time you check code into a repo, all the tests are run and that code, that PR is not accepted until all those tests have passed. And so my friend Mark Roddy, who's not here, he's a former data engineer at Etsy, now he's at Rokana. He wrote this amazing core answer about how you test stochastic algorithms from a data engineering standpoint. He jokes that he's the J.D. Salinger of Quora because he just wrote that one answer like 3 years ago and never used Quora after that. But that periodically, like, it'll get 50 retweets, just because someone else found it. So it's actually a really interesting answer. If you're thinking about this more from the software engineering standpoint, like, how do I throw tests on top of stochastic algorithms? I recommend visiting bit.ly/testing_algorithms. All right, questions? Yes?
Okay, so one of the pain points I have is testing plotting code, basically.
Oof.
Because you have one option, which is mock out all these global annoying functions.
Yep.
And you have another option, which is image comparison, but that's expensive.
Hugely.
I was wondering if there's a good middle ground of almost like a textual representation of a plot, making sure that your plotting function doesn't break.
That's a great question. Rob Story, do you have anything about that? I actually don't know, but if you want to hang around afterwards, I think maybe some people might have some ideas about that. Rob, do you actually have some ideas about that?
Yeah, we can talk about it.
Cool. All right. Yes?
I was wondering about your thoughts maybe on, I I guess, the pros and cons of mocking data versus taking like real data and then using it to build a test?
Totally, yeah. I think the answer is probably both. The key to a lot of testing is that you want it to be fast and automatic, because if tests take a long time to run, you're not going to do it. Right? So if you have to hit a database every time, and say it's 2 o'clock in the afternoon, that's like the busiest time in the office, and you don't have like very high priority or something like that, you're gonna not test on new data, because you're just gonna use the data that you pulled this morning when it was fast and whatever. I think a combination for sure. So I think when you're kind of writing a lot of the ETL functions for the first time, it makes sense to use some randomly generated data and then pull in real data once those tests are passing and figure out where to go from there. But obviously the real data is what you are going to be using. So I wouldn't recommend ever using all randomly generated data and then see you in deployment, so. Yeah.
So the hypothesis library looked really cool.
Yeah, it is.
But I noticed in your example, you had to re-implement your function to test it.
That's a great question. That is because of the contrived test that I kind of have here, yeah.
Is that a problem you've encountered a lot, or is it in the real world something you can avoid?
Yeah, that's a really good question. It is something you can avoid if you're careful about it, but if you're testing the very core functionality about it, like there aren't many things I would test about this function, right? Like, so let's say, kind of a contrived example is testing that x plus y equals y plus x. Like there's no other way to test that other than to write that out again. But I would certainly hope that your tests are not re-implementing your code, because then probably what happens is that your code is complicated and yeah, so.
So I guess where do you get your known value prompts? Because the standard paradigm is assert that this
Right.
is the known value. So
Yeah. Oh no, okay, sorry, I see what you're saying. Yeah, so excellent question. So we could, in this particular example, I don't know how you would get around that. I haven't used it as much as I would like. I think it's exciting, but haven't used it as much as I would like. That's a good question. I'm happy to follow up with you about it. Yeah.
So I guess a practical, normally I feel terrible about all this stuff. The only thing I felt good about lately was that I wrote a test that took my training data and reran it through my model, and I asserted that my model was overfit to my training data.
Nice.
So at least know the model's not broken.
Yeah, that's great. Don't feel terrible about that.
That's the one thing I felt good about.
Oh, sorry, yeah. Well, feel good about that then. Yeah.
yeah, sort of on a related thing, maybe from my experience in sort of scientific scenarios, often when you build a model, you want the model fitting procedure to work on some data that we've simulated.
Yep.
Getting into this, some assumptions about the world. And I wonder whether that misses the point that you made about modeling, whether our definition of model is different.
Yeah, no, I don't think those two things are in contrast necessarily. I think that, so if you're using simulated data, what you want to test then is you want to make sure that the simulated data all the assumptions you've made about what that data is going to look like are met. The model itself then, this gets into the trickier, like how do you know if a model that you've built on simulated data is correct unless you have previous real data that you use the same kind of model on. That's a kind of infinite recursion problem, right? Like how is my model correct using simulated data? But I don't think those two things are in contrast. And so when I say testing the model, like I mean, let's say are you implementing the model from like primitives, or are you using an existing package? Like what does that look like for you usually?
It's usually some mathematical function.
Right.
It has very few parameters.
Yep.
I'm simulating data with those parameters baked in, and I just want my model figures to within some tolerance, to sort of pull back those parameters.
Oh yeah, so you want to recover the parameters that are, yeah, absolutely.
It doesn't necessarily test whether it works on actual data. That I'll do separately just by evaluating them.
Yeah.
But for the purpose of knowing that the model fitting procedure,
Yeah, I think that, yeah. And then you want to make some hard assertions that data should look like this. I think that's totally fair, yeah. I'm not proposing that you should get rid of all values baked in. I'm just saying I think it's a more flexible workflow for a lot of traditional modeling questions. But that seems like a reasonable case for, you want a hard assertion that this data is equal to this data, essentially. That makes sense to me. Any other questions? Yeah.
How do you test the data at a more fundamental level in terms of the pipeline? Like, let's say you depend on some other API or some data source, and all of a sudden that data source is broken in a way that is not obvious.
So that is a really good question, because if the data source is broken in a way that's not obvious, then you might not know it's broken. It's just that your model performance is now going to look different than it did in the past, and you're not going to know why, right? So I think this gets back kind of to a similar question. If you have, say, let's say you have some assertions you can make like that the data will be noisy, right? But it should always be within a couple of standard deviations of some given value, or it should always be within some range. You can make those assertions, but if the data source is broken somehow and still meets those criteria, that's going to be very tricky to diagnose. In that case, what I would say is you need to make sure the tests that are implemented on where the data is coming from are implemented correctly, right? So like that data is coming from somewhere else. And so if it's being transformed in some way before it gets to the API, then you don't have control over that, but hopefully that's being tested on their end. So that's when you need to reach out to them and say, what gives, right? Anyone else? All right, well, thank you very much for coming out, and I'm happy to answer questions afterwards.